Now that we've had exposure to the fundamental theorem of calculus part 1, let's talk about the fundamental theorem of calculus part 2. Now, fundamental theorem of calculus part 1 demonstrated to us that if you differentiate a definite integral function, that for all intents and purposes the derivative will cancel out the definite integral. The fundamental theorem of calculus part 2 is going to reverse that. Rather than having a derivative on the outside and an integral on the inside, part 2 will state the following. If we're interested in evaluating the definite integral from a to b of f of x dx, this is going to be equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f. Now, something that we've investigated a couple times throughout the course of these videos has been the area that lies between 0 and 1 of x squared dx. We estimated this using finite values of n. We evaluated this as a Riemann sum. And now we're going to use the fundamental theorem of calculus part 2 for this. So fundamental theorem of calculus part 2 says find any antiderivative of x squared. Applying the power rule for antiderivatives, that would be 1/3 times x raised to the third power. The notation that we use for this is we're going to put our bounds for the integral on the right-hand side to indicate I'm going to plug in this value to this function, then I'm going to plug in this value to this function and subtract the result. So this will be 1/3 of 1 cubed minus 1/3 of 0 cubed for a final answer of 1/3. Now just take a moment to consider the line that I put here, and take a moment to consider the Riemann sum that we set up last week. If you feel angry, I can't say I blame you. Now, I do want to go over the proof of the fundamental theorem of calculus part 2, and it is based off of the fundamental theorem of calculus part 1. So, first things first, I'm going to define a function. I would like to define, no, we need to use a different thing for this. Let's do, I guess we can do this. So, yeah, let's do it this way. So we're going to define, sorry guys, little mental block. We're going to define g of x. We're going to define it to be the definite integral from a to x of f of t dt. Now, according to the fundamental theorem of calculus part 1, we have that g prime of x is equal to f of x. Little yeet going on there. We're also going to say let capital F be any antiderivative of little f. We can interpret that by the definition of antiderivative to mean that capital F prime of x is equal to little f of x. Now there's a theorem back in chapter 4 that said anytime the derivatives of two different functions are equal to the same thing, then those two things have to be equal to each other, with the exception of perhaps a constant. So that lets us know that capital G of x is going to be equal to capital F of x plus some constant. Now plugging in the definition of what g of x is, that lets us know that the definite integral from a to x of f of t dt is equal to capital F of x plus c. Now what we're going to do is generate an initial condition by saying let's plug in x equals a. If we plug in x equals a, we're going to get the definite integral from a to a of f of t dt is equal to capital F of a plus a constant. Now, based off of one of the properties of integration, though, the definite integral from a to a, it doesn't matter what this is guaranteed to be equal to 0. So if that's guaranteed to be equal to 0, that lets us know that 0 is going to be equal to capital F of a plus c. Solving for c lets us know that c is going to be equal to negative capital F of a. I'm going to take this value of c and plug it back in right here. That is going to give us the following statement. The definite integral from a to x of f of t dt is equal to capital F of x minus capital F of a. Then I'm going to plug in x equals b, and we will get exactly our desired result. That'll be the definite integral from a to b of f of t dt is equal to capital F of b minus capital F of a. Now, technically, this isn't exactly the same as what we said on the previous page due to the fact that the variable that we're using here is t rather than x. The thing that I would point out is that our final answer is going to be a number, so the variable that we use is going to be irrelevant. I could say definite integral from a to b of f of t dt. I could say the definite integral from a to b of f of x dx. I could say the definite integral from a to b of f of u du. I could do f of theta d theta. The only important thing in all of these definite integrals is that whatever variable we're using here has to match the variable that we see at the end of the integral. This is referred to as the differential. So the independent variable must match the differential. Independent variable matches the differential, and the independent variable matches the differential. More examples to come shortly.